In this video we're going to consider features in CasaXPS that relate to the fitting of doublet peaks in XPS spectra. The sample is germanium oxide on germanium, and we have doublet peaks in the form of germanium 2p. We also have germanium 3p, these are both p orbitals, and also there is a germanium 3d. So there's lots of evidence within these data of chemical state and also doublet peak separation that varies depending on the core level that we analyze. These germanium data are useful when we consider peak models because we have three different examples and they all have different characteristics. So if I now display all three together, we can see that we've got one example where the doublet pair separation is significant and is far greater than the chemical state separation. We have another example in the form of germanium 3d where the doublet pair separation is less significant and indeed is quite difficult to identify from these data, but the chemical state separation is significant, so we can clearly see the two chemical states. Now we have a third example, the germanium 3p, where we have correlated information that is correlated in terms of the doublet pair separation and also the chemical state separation. The first spectrum that we'll consider is the germanium 2p. And the reason that I'd like to start with the germanium 2p is because it demonstrates the importance of having a survey measurement to accompany high resolution data. On the face of it, the data set includes a set of measurements that looks fairly comprehensive. We've got the germanium spectra from each of the possible transitions that are associated with germanium, and we've also got an oxygen. But what we do not have is any information from these narrow scan spectra that relates to contamination, in particular carbon, because carbon is very relevant to the fitting of germanium 2p. A survey measurement measured from this sample allows the context for these narrow scan spectra to be established. In particular, we can observe that there is a peak here that does not belong to the germanium or the oxygen. We can see this by making use of the element library, and if we select oxygen and germanium, these are the expected elements, so we see that we've got an oxygen peak, an Auger from oxygen, germanium, germanium Auger, and the peak that definitely is not matched is this one here. These others are probably Auger peaks from germanium, but this peak here is not. It is carbon. You often find contamination of samples that introduce a carbon peak, and because we can see the carbon 1s, we know that there must be a carbon Auger. And when we observe more closely, we see that the carbon Auger is somewhere in the region of these germanium peaks. So when we construct a peak model for germanium 2p, we must be aware that beneath the signal that represents germanium 2p, there must also be carbon Auger. A typical peak model will be designed based on high resolution data. And in this case, we have data that has been collected using ParsNG40. We can see this if we display the acquisition parameters that are saved within the VAMAS block. So we've got ParsNG40, it tells us that the energy step size is 0.1 and that 851 data channels were used to collect this spectrum. And to some extent this explains why the noise appears so high in these data, is that the acquisition time has been spread over a lot of data channels. So while the signal within this spectrum is relatively good, it has been distributed in such a way that we see more noise than we might expect, typical for a ParsNG40 spectrum from germanium 2p. The level of noise we see in these data is also influenced by the background itself, and this is much clearer if we measure the intensity of the signal relative to 0. And you can see now that these peaks sit on a relatively high background. For pulse counted data, of which this is an example, the noise that we see in each data bin is related to the square root of the counts per bin. So for a high background, we would expect to see a relatively high noise compared to a lower background. The reason that the noise level in data is important is because the precision with which we can measure a peak area is a function of the noise in the data. And the reason for that is that the background must be calculated based on the noise at either end of the interval about which we're going to create a peak model. And since the precision with which we can specify the peak depends on the background definition, and the peak model is constructed from a set of components that sit on top of a background, the background will also alter the relationship between peaks within a peak model. The first step in creating a peak model is defining the interval of which the peak model will be defined. And this is done using the regions property page. And when a background is created, we can adjust the region limits and target a specific set of peaks within the data envelope. I'm going to start by illustrating what the background might look like if we use a Shirley background. A Shirley background is calculated from the data. So this means that the shapes that we see here are prescribed by the algorithm and the number and shape of peaks within this interval. Let me just adjust the display. You can see that there are characteristic S-type shapes that we see beneath these peaks. And the shapes are generated regardless of the physical origin of these peaks. So elemental peaks and oxide peaks are dealt with in exactly the same way by a Shirley background. It's already apparent by eye that the step across these peaks here that represent the germanium 2p3 halves is different from the step we see here for the 1/2. And the reason there is an apparent difference in the background can be seen if we consider data that were collected from a gold sample that was just placed in the analyzer and measured without cleaning. And the carbon contamination on the surface of this gold sample has produced an Auger peak in this proportion. So if we consider what that would look like if we translated from the carbon peak that we have here to the Auger peak that we have here in this germanium sample, you can see that there ought to be an Auger peak of significant intensity that sits beneath these germanium 2p doublets, and in particular beneath the germanium 2p3 halves peak. The conclusion that we should draw from this comparison between adventitious carbon on gold versus adventitious carbon on germanium is that we can't trust a simple background type to represent the signal beneath the germanium 2p3 halves peaks. However, when we look at the germanium 1/2 peak, there's a very small rise in the background, and so on face value it would appear that we can use a relatively simple background to model these data, and therefore construct a simple peak model which can potentially be used to describe what should appear in relation to these germanium 2p3 halves. So we'll target the background on the 1/2 doublet, and we'll then make use of the average width to improve the quality of the background and how it relates to the intensity of the data. So I've now got a Shirley background here, which may or may not be appropriate for these data. We'll establish that after we've first of all created a pair of peaks representing the elemental and the oxide. Now if I'm going to use the 1/2 doublet, I should specify I've got the 1/2 doublet, and assuming that I'm not going to make use of the 3/2 signal, I will change the RSF in this region on the basis that if I wanted to use this in quantification, I need the appropriate RSF that is scaling these data according to a 1/2 doublet intensity. Peaks are added to this peak model using the component property page. And since the background is only defined over this germanium 2p 1/2 peak, when I press the create button, a peak is inserted, and I can move this peak, as I will do, to the position for the elemental form, and again I'm going to use an RSF that corresponds to the 1/2 peak for this component, and then I can copy this and paste. So I now have two components. I wish to move one into the position of the oxide, so I need to label this oxide, and the first component will be the elemental peak. I can say fit, and if we zoom in we can see that we have a rudimentary peak model that is fitting these data. The quality of a peak fit is often assessed by looking at the residual standard deviation and the uniformity of the residual itself, and in both cases here we have high quality in terms of data reproduction. The question, however, is, are we really creating quality output by fitting these data using a pair of peaks? And in this instance we can answer the question by simply looking at the ability of this background to measure the area of the peak that we are now attempting to fit using a pair of peaks. We can calculate the relative error in the peak area using a Monte Carlo procedure that is available on the regions property page, where it says calculate error bars, and when pressed a Monte Carlo simulation is performed, and the uncertainty in the peak area that one would expect due to noise varying the behavior of this background is reported here in the regions property page. And we can also add to the display the relative error. So here we can see that the relative error that is calculated, let me turn off the residual so we can see it, the relative error in the area of the peak as calculated by this region is 5%. It's worth putting the uncertainty that we've calculated here in the context of other peaks from germanium. The reason that this is 5% is because we have a small peak sat on a large background. And if we compare this to a germanium 3D peak, which is a larger peak on a lower background, we find that the absolute error is smaller and the relative error is 0.5. It's a factor of 10 different between the germanium 3D and the germanium 2P 1/2 peak. So the question should be asked whether it's worth analyzing these data in this state at all. So although I've constructed a peak model, there is some doubt whether this peak model has value in terms of quantification. Qualitatively, we can certainly see from this peak model that the oxide peak is significantly more than the elemental peak. And that's worth noting because when we look at the germanium 3D peak, we find a very large elemental peak and a relatively small oxide peak. So the peak model for germanium 2P 1/2, even if it does not provide the top quality data that we would like on the basis of the signal to noise we have in these data, the ratio of these peaks are providing some physical information about this particular sample. The reason that we see a difference between the relative intensity of the elemental and the oxide peaks between germanium 2P and germanium 3D from a sample that is a thin film of oxide on germanium is the sampling depth changes as a function of the kinetic energy. And this is illustrated here where the germanium oxide is a surface layer, and so it attenuates signal from the germanium that is beneath this oxide layer. So when we have a low kinetic energy, the attenuation is far greater than at the high kinetic energy. So the three attenuation lengths from which XPS samples information is shallower and includes more of the oxide layer for the low kinetic energy electrons, and at the high kinetic energy the three attenuation lengths extends deeper into the germanium sample, and therefore we see more elemental germanium. We'll now construct a peak model for the germanium 3D. I'll do this by creating a new window, and then we'll display the germanium 3D in the full tile. You can see that if I cascade these, that in fact I've got now 3 views into the same data file. One is the empty data file, and the others are either the survey measurement or the germanium 3D. And these new windows, and you can see the index 1, 2, 3, allow me to view the same data file using different windows, so I can work on this germanium 3D and still maintain the display state for the survey spectrum, or where I've got all 3 data displayed. Given the arrangement of these windows within CasaXPS, the germanium 3D is currently being displayed in the active tile in the active window. This is the active tile because it has the banner above the data, so the title is the indication that this is the active tile in this window, and this is the active window because this is the window with focus. And when I raise the quantification parameters dialog window, it will be this window and this tile that will be processed when I create a region. Now, because these are all windows into the same data file, the file with the index 3 is also displaying the germanium 3D, and it is now the active tile in the active window because I gave this window focus. So when I create a region is created on this germanium 3D data, and because they're both looking at the same data file, the tile that now has focus is the germanium 3D data in the window with index 1, and it's the same data, so it's displaying the same quantification region. So we'll create a peak model based on this region here. Now I'm going to adjust the region so that I can see both of these tram lines inside the data, and that ensures that the average width is taking effect. I'm going to do this both sides, so I can see tram lines both sides, and they correspond to an average width of 5, which requires 5 points outside and 5 points inside of the region in order to take effect, and then average the data so that we have a more stable start and end to the background. This is important for any peak model. So the next step is to create components, and these components are entered. I can adjust with the mouse and then create new components, and the idea is that this is a doublet pair, so I'm expecting there to be 2 peaks here, even though it's quite difficult to see that there really are 2 peaks here on the basis of the data envelope. And this is because we've used parse energy 40 to acquire these data, and the energy resolution isn't quite good enough to see these individual component peaks. I'm going to repeat this process. I'm going to do this actually by copying these 2 peaks, pasting, and then using the mouse to move the peaks into the position where I anticipate the oxide peaks to be. If I say fit, I end up with a peak fit that really does not reflect the physical meaning of these 4 peaks. I need to have the ratio of these peaks to be in the right proportions for a 3D doublet. The existence of doublet peaks in XPS is because the XPS process creates a hole in a set of electrons that initially all have the same energy. So in the case of the d orbitals, there are 10 electrons all with the same energy, but once an electron is emitted, the coupling of the spin and the orbit then means that in the ion that is created there are 2 different energy levels possible, and the states that are available within the ion means that the 10 states that were all equivalent in the atom are split into 2 sets. 6 are assigned a quantum number 5 halves, and the 5 halves indicates all 6 electrons have the same energy, normally speaking, and then there are 4 that are assigned the quantum number 3 halves, indicating there's a different energy for 4 electrons. So we ought to see a split in energy, and we ought to see a difference in the intensity of these two peaks in the ratio 6:4. The objective in constructing this peak model is to measure the relative area of the elemental and the oxide peaks. And this is in contrast to the construction of the peak model in terms of doublet peaks. The doublet peaks, we do know a physical relationship should exist between these areas, and we can introduce these physical relationships by use of constraints. If we were to use constraints to apply an area relationship between chemical states, then we would lose information that we're hoping to gain. So there is this difference between introducing constraints for doublet peaks and applying constraints to peaks from different chemical state. In order to introduce these parameter constraints, we need to select the parameter for the area in column B, which represents the 3/2 in this doublet pair, and we know that the area of this peak ought to be in the ratio of 4:6 with respect to the component in column A. So having entered A star 4 divided by 6 and press return, we end up with the area relationship enforced by this constraint. So when optimization is performed during the fit operation, the peaks now adjust and they take up a relationship in terms of the doublet peak areas that are physically meaningful. We need to do the same for these oxide peaks. So in this case, the 3/2 peak, which ought to be at a lower kinetic energy, higher binding energy, is in column D, and I'm going to specify the partner to this doublet, which is in column C, so that the ratio of these areas is 4:6 also. And then applying the fit button, we ought to find a similarly adjusted pair of peaks with areas appropriate for a doublet pair. The only problem is that the data and these 4 peaks and a background currently introduces a shape for these oxide peaks which is probably incorrect. The ratio of these peaks is correct in terms of area, but the ratio of the 4/2 maximum is incorrect. The mathematics of optimization produces a peak fit based on the constraints that we've already applied, but also based on the line shapes that we define within the peak model. At the moment we have line shapes that are all specified as a Voigt type function. What I'm going to do now is change the Voigt type function into a pure Voigt function by specifying the first parameter as 1 and the second parameter as a large number representing the width of a Gaussian that is convoluted with a Lorentzian. And this will introduce wings into the shapes of these components. And I can apply this line shape to all of these components if I enter equal and then press return. This produces a different data envelope because we now have different component shapes. So I need to say fit once again and then observe how these new line shapes alter the shapes of the peaks when fitted to the data. And while there wasn't a great deal of change here, there was some change, and you can see that the width and the position of this oxide peak has altered simply by choosing a different line shape. It's worth noting that the background also influences the shapes that are available for the fitting of these data, so there is an interplay between line shape and background. For the moment we'll leave this as a Shirley background and then make adjustments to these elemental peaks on the basis that carbon in a graphitic form, elemental silicon, both provide evidence that there may be some asymmetry that could be assigned to these types of germanium peaks. So in order to do this, we'll introduce a prefix, and this prefix represents a degree of asymmetry that can be introduced into these components, and we want to do this only for the elemental peaks. So in the first instance I'll apply asymmetry to one of these, and then I'm going to make use of the component index so that I can target the line shapes to specific components in this peak model. I do not want to apply the same asymmetry to to these oxide peaks. So in order to specify that I just want to update these elemental peaks with this line shape, I've given them the same component index, which is different from the oxide peaks. And now, rather than saying equals, if I put hash and then return, I update just the elemental peaks. There are only two in this case that I wanted to update, but nevertheless this mechanism will apply to multiple peaks. Having created these asymmetric peaks, the envelope once again changes, and then I press the fit button, and yet again the introduction of a new line shape is moving this oxide peak more in the direction of where one might expect this oxide peak to reside. The idea is that the separation of these two peaks in the oxide ought to be similar to the separation of these doublet peaks in the elemental form. So the fact that it's moving towards this smaller peak is a positive step in trying to produce a physically meaningful model. The definition of the background is part of the peak model, and we can see here from the residual that the peak model is struggling at either limits of this energy interval. So what we can do is zoom in, and while the component property page is topmost, if we point at the start of this energy interval at the background and then hold the left mouse button down to drag, we can make an adjustment that improves the quality of this fit at this point here. And we can do a similar adjustment at the end, and the end is slightly more complicated in the sense that there ought to be an oxygen 2s peak somewhere in this region, and it will interfere with the definition of this background. So there's a certain element of guesswork that is inevitable when you have interference of low level, although there must be some oxygen here because we have the oxide peak. So the adjustments of the background are significant to the definition of this peak model, and they are complicated by the nature of these types of data. Having adjusted the background and ensured that we've got data reproduction at this point and this point, we've lost some of the data reproduction here because we've moved the background. So we have to press the fit button again. Let's zoom out and say fit. And we can now see the data reproduction is good. We have a good quality of residual, and the residual standard deviation is consistent with pulse counted data. So at this point we may conclude that we've got a peak model that is representative of the elemental germanium and the oxide, so we have a means of measuring the ratio of these two chemical states. Although good data reproduction suggests this is a feasible solution, it doesn't necessarily mean to say that this is the absolute solution, that there may be other factors involved that would alter the shape of these peaks and therefore the ratio of these peaks. An example of this would be to look at the germanium 3p, where the correlation of information between the chemical state and the doublet pairs means that we can interpret these data in different ways depending on how we choose, for example, the background. In this case, the background is varying very little, and we end up with a ratio of 75 to 25 for the elemental versus the oxide. However, we can also create a peak model where we introduce a background that has Shirley type shape, and this produces a ratio of 81 to 19. So these variations are a consequence of how we choose the constraints and how we choose the backgrounds.